Hey everyone, thanks for coming back to D-News Plus this week for a very special week on the LHC in CERN. And if you don't know what that means, you should go back and watch episode 1, because I explain what all of those groups of letters mean and how important they are and how excited I am. Back in episode 1, I explained what the Large Hadron Collider is and what linear accelerators are and how all of this stuff comes together to build this biggest machine in the world. Today we're going to talk to somebody who works on it. Works on an experiment that's sitting on the LHC ring. Her name is Talika Bose. She is an associate professor at Boston University, and she does this really cool thing, and I would explain it to you, but I think it's better to just let her do that. So, give us a little context. Where exactly are we right now?
Okay. So we are at the ring that the LHC lies on, the Large Hadron Collider. This is about a 27-kilometer circumference. This is very large. It straddles the Swiss-French border. And at different points of the ring, we have different experiments located. And at a certain point, this is in the town of Cessy in France, we have the location of the CMS experiment. We are right now over ground. The actual detector is about 100 meters under, which is
that thing?
Behind there.
It's quite large.
It's under, yes. It is very, very large. This is about 3 stories, and so, it's called CMS, compact muon solenoid. However, it really is not compact. Right. It's a relative term, as you can see. Nothing of that size is compact. And it's just that the design philosophy was to make something that was all very, very dense, made of materials all together without it being sort of lightweight. Mm-hmm. And that's why the name came about. And we can't actually go down underneath at the moment. We are in the process of a new run, which is collecting data. So we are here where a lot of the initial installation was done in terms of getting the detectors ready such that they would then be taken down. So CMS is very special in the way that all the different parts of CMS were constructed over ground and in chunks, and then slowly each of these chunks were lowered through this big hole into the cavern, and then all of the pieces came together, and voila, we had CMS.
Oh my gosh, that's so cool. So there's a tunnel down here somewhere that all the way down below us. How far below us is the cavern?
It's about 100 meters down below from here.
That's far.
And so it's
way down there.
It's way down there.
Why is it so far down?
So you want to be essentially away. You want to be in an area which doesn't have a lot of. It's isolated, so you want to be maintaining these beam pipes which go around where the proton beams are going around, and you want to isolate it from any kind of movement, etc. And so you want it to be, of course, it was also determined by geography and where they could build such a tunnel, mm-hmm. because if you were to imagine if this was actually over ground, then it would be obstructing things. But now the tunnel goes underneath, however, there are farms and there are houses, and I mean the area is being used up.
Yeah,
and,
it seems very beautiful, very rural almost.
Right.
We saw a bunch of cows on our way here. That was crazy. And underneath is one of the most incredible science experiments that we've done yet.
That's right.
As a people.
And there are also side benefits. For example, we also wanted to be down underground to sort of minimize some of the backgrounds that we get from normal atmospheric processes. For example, we have cosmic ray muons.
Yeah.
So cosmic rays, protons, etc., interacting in the atmosphere, creating showers of particles in which there are muons. These then travel all the way, and they in principle can enter our detector, and they are background processes to our regular searches, and by putting it deep underneath we can minimize how much gets there.
Yeah, you wouldn't want to kind of distract from your experiment.
That's
by
right.
Getting this background in there. That's pretty crazy. So how many kind of data points are you looking at every experiment? Because the protons are flying around this ring and they're colliding with each other. How often?
So they collide about 25 nanoseconds. So every 25 nanoseconds. And it's not a single proton that's colliding with another proton. These are bunches of protons. And each bunch of protons has about 10 to the power 11 protons. So you have a bunch colliding with another bunch. You may have a proton here and a proton here, which has a hard, what we call scattering, a hard event, and out of that comes out a whole mess of particles. But in addition, because there are other protons in this bunch, they could also have interactions, and it's a
Oh my
very
gosh.
complicated, messy environment.
Yeah.
And all of this is happening every 25 nanoseconds.
Wow. So how do you decide? I mean, the trigger, I guess, is how you decide which ones of those are the most important.
That's right.
So you're essentially creating this sample of data from a wider data set that you're making constantly. Wow. So what's the source of all of these protons? Where do those come from?
So it is a multi-step process. It actually starts very simply, bottle of hydrogen gas.
That's it?
Which, yes.
Wow.
So you start with a bottle of hydrogen gas, and essentially you remove the electrons. You remove the electrons, you're left with the proton, and then you take the proton through a series of accelerators which give it just a little bit more energy, and then another one which gives it a little bit more energy, and in this process you're able to get it to very, very high energies. And this is currently the highest energy accelerator in the world. So you have about protons with what we call 6.5 trillion electron volts going around this way, another beam of protons, same energy going around this way. And it sort of takes, a little bit of time to get them to this kind of energy over, of order of, minutes, 20 minutes or so. And then once they're there, they're whizzing around like this. And what they do is, so it's an actually interesting system because we have different kinds. How do you make protons go around in a circle,
yeah.
right? That's the first question. So we have magnets, very specialized magnets, dipole magnets, and their job is to essentially, take these particles and steer them. And so what you have at the same time initially is an accelerator, which is sort of increasing their energy, and then steering them such that they go around. And this comes from electromagnetism, a charged particle moving through a magnetic field. It experiences a force, and depending on,
Physics.
it goes around, yes.
Yeah.
And now they are actually two what we call beam pipes, and one beam of protons is going in this direction in one, and the other beam pipe has the other beam of protons going in the opposite direction. And we do that because we don't want these protons colliding just randomly
when you're not watching.
That's right, because then we will lose, intensity. So these tubes are maintained at extremely high vacuum because you don't want to lose the intensity of the proton beam. Then at very specific points along the ring, what we have is we bring essentially the protons together, the two beams together. This is done by another set of magnets. The previous set, which sort of steered them, these are dipole magnets, and then these are what are called quadrupole magnets, and their job is to essentially focus the two beams, which are moving in opposite directions, to collide at a central point.
And that's where one of these
That's
is.
right. It's right there
Right
in the middle of
middle.
the circle, as you see, the innermost circle. That's where the beam pipe is. That's where the collision is happening. And what you do is, all around this collision point, you instrument it with
all of these things.
detectors.
So in the middle, you're detecting some things with all of these various instruments, and that way, I mean, it's almost like setting up as many cameras as possible around a crash test of a macro-sized thing,
That's right.
So you can get all of the different data points and see it from all the different angles, because it's only going to happen, maybe a really interesting one only might happen once.
That's right. So you have to make sure you know that just in case one detector misses it, you have another detector that helps catch it.
Right.
Also, what we have is actually, it's not a single detector. We call it, the CMS detector. However, it has different what we call sub-detectors, and each of these has special properties, some of which are looking for special kinds of particles. So basically, right outside the beam pipe or the ring, we have what are called the tracking detectors, and their job is essentially to track the path of a particle as it goes through material.
Any particle.
That's right.
Just like, here's something, it's going that way.
That's right. In particular, what we are looking for is a charged particle, because they are made of material, in our case silicon, where you can actually track the path of this charged particle as it goes through. And this way you know if it curved like this, if it curved like that, because the other important part of the CMS experiment is that it has an extremely strong, big, large magnet. So it's a compact muon solenoid. So the solenoid term comes from the most central part of the detector design, which is this 4 Tesla solenoid magnet.
That's a lot.
And so it's one of the largest magnets of its kind ever built. And so why? So the idea was that if you have a large magnetic field, you can actually get very good momentum resolution. That is, you can measure momentum, especially of high momentum particles, very well. And so we use that by having this large magnetic field, because what will happen is, again, electricity and magnetism, charged particle goes through a magnetic field, it's going to curve in a certain way. And there are two important pieces of information that we get from this. One is whether it's curving this way or if it's curving that way. That tells us whether it's positively charged or negatively charged, depending on the orientation of the magnet, etc. And then how large is the radius of curvature? Because it could be curving like this, or it could be curving in a much larger radius. And this has a direct relationship with essentially what the velocity and consequently what the momentum of the particle is. So using this information from the inner tracking detector.
That's just the middle.
Just
That's
the middle. So how is it useful? Because what we've seen is we can get momentum, we can get charge, and the presence of the tracker also allows us to differentiate whether or not this is a charged particle or a neutral particle. Because a neutral particle doesn't do all of this. It was not going to leave tracks in the tracking detector. Of course, what that means is you need to have another detector to catch and identify these neutral particles. So then we go to the surrounding detector. This is the electromagnetic calorimeter, and its main purpose is to measure the energy of particles that interact electromagnetically. And these are primarily electrons, it's antiparticle, the positron, and photons.
Yeah.
So now this is the interesting way in which you can differentiate this, because your electron and your positron, they are charged particles. So they would have left a track through the tracker, and now they're going to come and deposit some energy in the electromagnetic calorimeter. So you have gotten its momentum, its charge, so you've identified whether it's an electron or a positron, and now you have its energy. So you've gotten some decent amount of information to identify electrons and positrons. The other particle that interacts electromagnetically is a photon. A photon is neutral.
Yeah.
So now for a photon, what you can do is you can measure energy in the electromagnetic calorimeter, but because it's neutral, it actually has not left a track in the tracking detector.
It's not curving, it's not,
That's
it's
right.
just shot out of there.
So if you see energy in the electromagnetic calorimeter, by looking at information in the tracking detector and you see no track, you have a photon. So now you have differentiated between electrons and positrons and photons.
Yeah.
So then what comes next? Well, there are other particles. They are what we call hadrons. These are more complicated particles such as protons, neutrons, kaons, pions. They don't interact electromagnetically, so in a way they will leave tracks in the tracking detector. They will go through the electromagnetic calorimeter, and we have specialized detectors called hadron calorimeters, where now they are going to deposit, they're going to shower and deposit their energy there. So now measuring that energy, looking at the information from the tracking detector, we have more information about these sort of particles.
Yeah.
Now, so this takes care of mostly all of the known sort of elementary standard model particles, and some, I guess, which are composites, such as the protons and neutrons. But now we have our muon, our naturally occurring cosmic ray muon. Now this actually it will leave a track as a charged particle. So again, you can get momentum and charge from the tracking detector. It does not interact much with the calorimeters, so it's going to sort of mostly whiz through it, and then we have specialized muon detectors at the outside where we are now going to measure the properties of the muon. So anything that gets out to the muon detectors is most likely a muon.
Whoa.
And so what you see out here, the outermost, that is the muon detector, which is sort of the last detector. And mostly everything has interacted before and you've measured, but muons are more elusive in that sense, and they make it all the way out to the muon detectors, and there we measure their properties.
And is that everything? I mean, did we capture it all? Did we get it all?
Good question, because we've captured most of the particles. However, there is another important particle which we don't actually detect in the detector, which is a neutrino. So a neutrino, this is a neutral particle. There is a neutrino corresponding to each of the lighter particles, electron, muon, and tau. And the neutrino is very weakly interacting. It does not interact much in our detector, and so essentially we wouldn't identify or detect it visibly. However, we can use physics principles, conservation of energy and momentum, that in the case where we see that there is some missing energy or missing momentum, that must be the case that the neutrino, which took away some of this.
Right.
And so any kind of missing momentum, we sort of attribute to this neutrino, which escaped undetected.
So if say, you put in 1 and you got out 0.99, you're like, oh, well, there was a neutrino in there.
That's
that was
right,
just
yeah.
a neutrino. This woman is super amazing and so interesting to listen to. I hope you agree. So make sure you subscribe and come back tomorrow for the second half of my conversation with Talika Bose. It's going to be really, really great. Let us know down in the comments if there's any other giant science experiments we should go visit, because so far this one seems to have worked out well. You can also come find the show over on Twitter. We're at DNews. I'm at Trace Dominguez. If you have any other questions about CERN or physics or LHC, I can try and answer them. Thanks for tuning in. We'll see you next time.